Hello, Calculus. This is Friday's edition. You'll be watching it Friday, Saturday, or Sunday. We are going to add a little bit to our understanding of the second fundamental theorem of calculus, and we're going to find the integral of a special expression. So, to do what we've learned about the fundamental theorem has been good, but I want to show you a complication that you're going to meet on your assignment. Suppose you're asked to find the derivative. Well, sometimes they write it like this. They'll say, here's the integral. We'll call it capital F of x. That's a typical way to express an integral. And let's say it goes from pi over 2 to, instead of x, let's say it goes to x cubed. So far, the ones I've asked you to do have just had a x variable there, and that's what the fundamental theorem demands. So what if it's not? What if it's an expression in x and not x? Alright, probably you can tell where this is going because you hear the chains rattling. So we're going to find f prime of x. And so that's going to be the derivative of this integral, which is second fundamental theorem territory. So let's go ahead and start working it out the long way. So I'm actually going to take this integral, and then I'm going to take the derivative of the result. And then we're going to see if we can quickly get from here to the answer. So I'll probably just do it once, and then you'll see how to do it. Alright, so the integral of cosine of t is sine of t, and it's evaluated from x to the third to pi over 2. So I'm going to put in sine of x cubed minus sine of pi over 2. It's always the upper limit of integration minus the lower. And that expression, sine of pi over 2, is a 1. So, but even if you didn't know that, you know it's a constant, and that'll get you through. So now I want to take the derivative of this with respect to x. So I'm going to get the derivative of sine of x to the third is going to be derivative of sine is cosine. And then the chain rule requires me to find the derivative of x cubed, which is 3x squared, and then a minus 0. So writing that out with this first and this second has the best eye appeal. So how can I get from this to this without any of this? What I can do is I can take this value and plunk it right into this expression. This expression is unchanged. So I'm going to get cosine of x cubed, and when this is not x, you just follow it with the chain rule for whatever that expression is. So that will get you there every time. So let's see if we can do 1 or 2 without any the inside work. Just remembering the process. So what if I have let's say I'm going from 0 to cosine x of the square root of t dt. So I want the derivative of this integral. I think this will get us there. So it's a fundamental theorem. So this is going to slide in and take the position of t. So we're going to get square root of cosine of x. And then it's going to be followed by the chain rule, because this is an x, it's an expression in x. It's going to be followed by its derivative. The derivative of cosine is minus the sine. And you're free to express that by the long way, by going ahead and taking the integral of this, putting in cosine of x minus the 0, and taking the derivative of the result. But it will get you right here. Alright, so I just wanted to show you that. And then there's another complication. It doesn't come up often, but I want you to be prepared. It's still on the second fundamental theorem, and it looks like this. All right. I want to find the derivative of this. All right. I'd like to use the fundamental theorem so I don't have to work out this integral, plug in this, subtract this, and find the derivative of the result. I'm hoping there's a quicker way using the fundamental theorem. However, as it's set up here, it fails as far as the fundamental theorem is set up, because this has to be a constant and this has to be an x or an expression in x. Turns out that we can fudge this a bit using properties of definite integrals. So I'm going to work on this. I'll come back and grab the fact that I have to take the derivative in a minute. So I want to get a constant into this picture. And I'm not sure what x is and x plus 3 is, but can you believe that there is some constant in between x and x plus 3? I can believe that. So x, there's some constant, I'll call it the constant c. Well, c shows up in other ways. I'll say a and x plus 3. No matter how close these are, x and x plus 3, there's going to be some value, some constant in between. So remembering the principles of definite integrals, we can, properties I call them, I can split this integral up into two. This one is going to go from x to a, and this one, guess what it's going to go from? A to x plus 3. Okay, so in order to, now this one still is not fit for the fundamental theorem because this had to be a constant and this had to be expression in x. So therefore, what can I do to this to flip these constants or these expressions around, the upper and lower limits of integration? Well, there was a property and it said if we have the value a here and b here, if you switch it and become ba, there's a negative sign out in front. So I'm going to use that property with a negative sign out in front. Then it does allow us to set these both up for the fundamental theorem. So I'm going to take the derivative of this one with respect to x and the derivative of this one with respect to x. So when I do that, I can't forget the negative sign. This x just runs into the value, and that one's done. And the derivative of this integral, this x plus 3, will go in for t. And what else? Then it's followed by the derivative of this, but the derivative of that is 1. I'll put it there to make sure you know to use the chain rule. Alright, so let's see, this is a negative 5x, a negative 1. This is a 5x and a 15. So the 5x's are gone, and 15 minus 1 is 14. Alright. I got a little bit different answer. Let me see if I actually had the same problem. Okay, there is a problem. I'm sorry, right here, this plus 1 got left out. So let me move this down. So when I slid the x plus 3 in for t, I forgot there's a plus 1 here. And it's still times 1 for the derivative of the chain rule, the derivative of that expression. So I have a 5x plus 15 plus 1. So I'm going to get a -1, and a 15 is a 14 plus 1 is a 15. Alright, now it's correct. Would you look at one more of these? How about you try this one and see if you can set it up. And we will finish it on the board on Monday. So we're going to do the same thing using this little trick of our properties of definite integrals. Alright, let's try the integral from -x to a, let's see. Alright, it starts out like this. -x to +x of the cube root of t dt. Alright, take a second and pause while you set it up with our special little trick. There must be a constant in between these two, so let's use that fact to split this into two integrals. And of course I'm finding the derivative of this whole thing. So -x is less than a, which is less than x. Alright, set it up, and we'll finish it on Monday, just set it up. Alright, so when you're set up, did you say that this first integral went from -x to a, cube root of t dt, and the second integral went from a to x. So it's sort of like if we had a picture and we had some function, we have -x to x, -x to x, and there's some value a in between. So we're going to find the integral from here to here, and then from a to x. So geometrically, it should make sense to you. Alright, so this follows the fundamental theorem with a constant here and an x here. This one almost does, so I'm going to switch these by putting a negative sign out in front. So we'll finish that and actually find the derivative of each of those. I just wanted you to use the trick here. And I don't want to take any more video time. So you can finish it now or on Monday. We'll do it again if you finish it now. Alright, the last thing I want to talk about is a special, the integral of a special expression. And there it is, the integral of 1 over x dx. The power rule says if you have the integral of x to the n dx, it equals x to the n plus 1 over n plus 1. We may have noticed that this has never shown up because that is x to the minus 1. And look what happened when we use the power rule. We get x to the minus 1 plus 1 over minus 1 plus 1, which is x to the 0. I'm okay with that. 0, I'm not okay with that. So the power rule only works when n is not equal to minus 1. So today we're going to talk about what is the integral when it is equal to minus 1. Alright. So the where we're going to go to find it, and you might have thought of it before I disclosed it, is the fact that in derivative land we learn to find the derivative of, well, do y equals, say y equals ln of x. What was y prime? Do you recall? It was 1 over x. So we've had that already. And then we upgraded it if y equals ln of some expression in x, which we call u, then the derivative was y equals ln of u, followed by the chain rule to u dx. Alright, so this is old news, so you can probably see what I'm setting you up to do. now we can think of the integral of this, because an integral will undo a derivative. So here's a derivative. So does this make sense that 1 over x dx will take you back to ln of x? The only thing is, this can be upgraded to an absolute value of x. And the reason that is, the log function looks like this, ln function, and it only uses values of x that are positive. However, if we put an absolute value here, it opens up a whole bunch of other possibilities. So we can use the negative x's because the absolute value will change them to positive and still get us an answer. So we're going to go ahead and do that. And notice x cannot equal 0. Alright, so that is a revelation for us, and I want to see if there's anything else I want to say about that tonight. I guess the only thing I'll say is let's upgrade it to a u. So if we have the integral of du dx, that's on the top. Oops, this wasn't right. Sorry about that. 1 over ln of u. Just like this. 1 over ln of u du dx. So this is on the top and this is on the bottom. Then we know that, it's still not right. The derivative of this is just like this, except it's u. So I'm going to take the integral of du dx, that's in the top, and u is on the bottom. So what is the derivative of that? ln, absolute value of u, plus c. So we're working backwards from a derivative that we knew, or I thought I knew, and now I know. And notice this can be written like this, the derivative of u over u. And then we can find that it's ln of the absolute value of u plus c. So write that down. We will use, we'll actually use it and be able to take a whole lot of integrals that up till now we couldn't do. Alright, so these will be introduced in our work eventually, very soon. So, till then, that's all for tonight, and I will catch you on Monday. Bye.